Okay, welcome everyone to Cloud Computing and Big Data, to lecture 12 today. It's about Docker and container management. And a lot of times in this course already, you have seen that we skipped a little bit that topic. We always said at the end of essentially all the lectures, or toward the end of the course, we will discuss it. And today is a day where we look a little bit more closer what Docker is, how it relates to container management and orchestration issues. And by this, you will also realize, having almost everything already from this course now basically learned, that this is really underneath or related to almost all topics you have seen before, especially if you zoom in, right? And the zoom in, I mean, even if you're on the SAAS level, maybe that you already learned the different levels, IAAS, PAAS, and SAAS, you can actually always, in a way, zoom into the services. You will look deeper in the technology in each of the different ones, and then you find suddenly the need for compute services, which often is either done by virtualization or basically on top of virtualization, then using a smart container strategy. So that's why we basically pointed to this lecture many times. It is, of course, a very technical topic, but I try to make it very interesting from applications and avoid a little bit the nitty details in terms of configuration, what you can do. But you learned already before that, of course, using MapReduce with containers or using deep learning with containers, you can configure it in lots of ways, also having used it in assignments. But before we go into lecture 12, let us just quickly review what we have done in the lecture before, which we also will pick up today again. If you remember, we looked a little bit in the IBM cloud for association rule mining, and very prominently with the Kubernetes. And Kubernetes is another topic we will talk about today, but in practical lecture 11.1, which was really thinking about using data mining and recommendation engines and systems in the cloud, we were basically using different types of clouds. Firstly, the Helmholtz Data Federation, which we will also reveal again in lecture 13, when we look a little bit more of how can you create your own private clouds with a technology called OpenStack. But we learned that essentially, if you get access to such clouds, sometimes not all the packages are in. And one packages that we installed together in this practical lecture was MLXtend, which is a very interesting Python library for association rule mining for different areas in machine learning. But the more broad learning message was really, if you face a cloud, there's still a possibility to tune it a little bit to your needs. And we come to this point exactly today, because the clouds generally try to be as, let's say, general as possible. Sometimes the very specific packages you need, and this is really a very specific package here, the MLXtend, is not there. So when you log in, you require it. You can install it with pip install, as we have seen MLXtend for an example on the command line. And this is, of course, also what you do in the assignment. But this is exactly the point where we'll see later as part in this course, lecture today, that containers try to solve that issue. So with containers, you would have perhaps an ML image, a container image we will look at, which has already scikit-learn, has already MLXtend, has already TensorFlow, you know, all the different packages you need for a machine learner included in one nice container image, which in turn then is a little bit different than virtualization images. And we will talk about it and make a case about why it's a little bit more beneficial to do so. However, in the last lecture, in practical lecture 11.1, you have seen there are essentially two different ways to do association rule mining, but they all capture the essence first of creating frequent item sets. So in one way or another, either you choose a priori or FP grows. Both are based on the same idea of looking on the frequent patterns in transactions from retail data, for instance, and then you essentially create them differently. We have seen through iterative lists using support and the item counts, we can use the a priori algorithm, and we have there an interesting example about bread, wine, eggs, a typical retail example, admittedly very low scale so that you can easily try it out and understand it much easier. And essentially you come then very quickly to the frequent item sets, and on top of these frequent item sets, you can now infer the association rules and build them. And what you get is, of course, then filter mechanisms with confidence and support, things which Shadi was alluding to a little bit in lecture 11, and myself also in practical lecture 01, actually at the beginning of the course. So even if you have the shopping lists and the association rules, where you say here, for instance, you can say people that actually buy bagel are very probably in a very, very high confidence here, also buying bread, which basically makes sense, right? However, you will find some of them which maybe have a very low confidence or basically have problems in the support, meaning how often they really are actually represented in the market basket transactions. This is, of course, then something where you have to filter out. In some ways, the shop owner will already know that. They will say, well, I know already that beer goes with diapers. But the point is that they can actually be so tuned that they look not only on the 2 item sets, but on the 3 item sets, as an example here. And as soon as it starts with 3 or 4 or 5 elements that are always bought together, the shop owner will rotate. So usually the human brain, if not, they do, for instance, other analysis, of course. The human brain usually cannot work that efficient anymore. And here you have really a benefit. If you go out of this course and you get, let's say, jobs in that area, you can easily use basically the script we provided to you as the assignment, tune it for your needs, use, of course, retail data from that shop. But then you're not done, right? Then it starts and you have to really tune a little bit, look at the support and confidence. There are more advanced options with lift and leverage and so on. And you have to be in an interaction, of course, with a shop owner. That then maybe do product placement in the shop. So they will put items more far away. In this example, maybe the bread and bagel should be not directly nearby each other. As I said, from practical experience, what this lecture was really about, usually the shop owners want to keep the customers as long as possible on the shopping floor, right? To get the chance of buying even more product that the eye maybe sees something where they're interested in. So apparently, of course, you have seen from Shadi, and then I'm making the case for it, that we want to scale it. That's why we do it in the HDF cloud. And basically, Shadi already in lecture 11 was showing that FP growth is then the answer to this, because a priori with the iterative approach is essentially not scalable if you have lots of millions of transactions that we face in a practical application, for instance. So there, you have to think about what are other ways to go to the association rules, which is to create, instead of just simple lists, a frequent pattern tree. And this is something which you see here on the bottom, and scales much, much nicer actually to very large data sets. But even then, you have seen that we have to make it in parallel. So we have to break it up, as Shadi was having on a couple of slides in lecture 11, and then essentially make it in parallel, these lists, and to then bring them together to create then in the end real lists that you need here, basically on the right-hand side, to convince the shop owners that onion and kidney beans, for instance, always go together. So in a way, that was one part of the lecture, which is a very important part of data mining, machine learning. We said also the largely overlapping, but we have also seen a very interesting other example, which is also directly related again to your assignment, the recommender engine. And this is really a powerful tool, and also, of course, a huge market. If you know, from Amazon Prime to Netflix, of course, a movie example, we a little bit in a toy scenario here looked in deeper. But think about that, you can use this Google Colab Cloud Notebook that you're working on and tune it to your needs, right? Then nothing prevents you from loading different data. You cannot just use movies there. You could basically put everything else you want to have maybe as a recommender engine. Let it be perfume in stores when you are working for this, or in supermarkets. Important is, of course, that you always have this rating matrix that we discussed. So this here in the middle, which in some cases might be not really ratings. We have seen in this trivial example, you maybe have to go with a point of saying seen and not seen. Or if you are in a supermarket or retail shop, you can transform it to 0 and 1 of saying bought and not bought. But the important thing is, of course, that this needs to be given to you. Otherwise, you cannot do the job. The other element of this is, as we also were discussing in the assignment, and that's why you really have to go through this in a walkthrough fashion, And really to understand that when you have two rare cases, for instance, if you think all the movies that are available, you have seen the drama bias in the data, right? Many people were looking drama, or a specific type of people were looking movies, like the students, and then they were rating and the others not. You always have a bias in the data. So this immediately brings you to things like sample out, class balance, or on the other end of the scale, try to do regularization. Then these effects may not be so dramatic. In a way, it's about these signals coming through. And when you have a very sparse matrix, for instance, then the signals are very low. And here you have to be also very careful. However, how that worked was essentially of thinking of having hidden features from these users learned and from these movies learned that we will essentially never know. So we led a little bit on a sad note that saying the learned embeddings here, the user metrics and the metrics on the movies that we with the dot product want to reach in order to learn essentially these matrices here bring us to some values, some numbers, maybe in the dimension of 30 even, being very precise maybe for a movie, but we don't really can explain them. These are learned embeddings in order to fit, and this is a point, fit your matrix that was given to you. And of course, this is an optimization problem. So here and there you would have other values coming out, but essentially then depending on which algorithms you use for optimization. If you remember, we used SGD, but of course you can have also other optimization algorithms here. We picked SGD largely because also you know it from previous lectures, right, from deep learning. And this was another example also of this. So you have seen that TensorFlow, if you remember, which was actually the example on the Google Colab cloud, was really based on TensorFlow, but we don't do deep learning here. But still, what TensorFlow can do very nicely is to operate on tensors, which are nothing else than multidimensional arrays or matrices that we need also here in our recommend example. And the other part, that was a twofold thing. The first one was thinking about the recommender. The other thing I wanted to bring across as a practical lecture, when you leave this course very soon, try to structure your projects around these processes. I tell it to my PhD students, to my master students, usually all the time. It makes sense to do so. And also if you're in a practical scenario, you will have different versions of the models. We will talk about this today, where containers can help there as well. But you will essentially have to document a lot of things also to be transparent to the one that gives you maybe the check. Usually it matters a little bit to copy paste some of the scripts you do in different versions to these different phases. That's why I think the CRISP-DM model, however completely tuned for industry and developed there, has also very much benefits for science. And it's really a practical tool. It takes some time to get used to it, but my recommendation is if you have a data science problem at hand, copy paste these different phases in a Google Doc or in some other document you want to do, and then every now and then update it. Of course, you have sometimes old information inside, but you maybe can then, from previous editions of work, see, the regularization parameter and this learning rate I already tried, but I came back after 3 months and completely forgot about it. So the documentation here and there in data science is important, not only for you, also you can actually show, let's say, people that give you money for this, why there's such a complexity. And exactly this complexity is also one part of the assignments to realize. When you think about that, we introduce more hyperparameters throughout the whole Google Colab scenario. We start very easy, but then suddenly we enter regularization in a different form of regularization. We add so-called regularization parameters. This is someone in a practical situation that nobody told you, right, how to pick that. So you have basically a problem of picking those parameters, and the more parameters you have, of course, it's going, very much quickly to a solution or to basically a problem that you cannot anytime use systematically anymore, because it's like regularization parameter times the number of the learning rates you try times the number of data set sum samples, etc., etc., etc. So in a way, we face here a deep learning problem. If you remember, we said also there, the hyperparameters are the biggest problem in machine learning when it comes to switching how many neurons, how many convolution operations, how many layers. So this is all related. In machine learning, by far the biggest problem, and perhaps one of the biggest area where you have to just take time. And the other area where you have to take time usually is then the evaluation, right? Sometimes, of course, it's a black box like in neural networks, but at least a little bit today, explainable AI is working on that to make more and more of this explainable. However, at the end of the assignment, you will see it's actually quite nice. We get good examples that actually seem to be not so much biased anymore. The selected topics and titles make sense. And in this particular example, you can really nicely see that in a way, evaluation helped us there to understand the problems of the drama bias or essentially the student bias and so on. So, but this was last lecture, and I think now it's time to go a little bit into the topic of today's lecture, which is also very practical in a way. I do it not really in an example because usually it's a very simple to understand topic and underneath many of the different aspects. And it's of course related when we just make the point that some of the deep learning algorithms and libraries we need, as well as the cloud data mining we had with MLX10, scikit-learn and so forth, can be nicely packaged in Docker, in containers at large. And with this, the idea of today is really thinking a little bit about this container management that we all the time in the course touched on. And it was, really from the beginning when we had the first MapReduce idea, we had different worker nodes that suddenly all had to do a little bit of MapReduce and install parts of it. So if you're an administrator and you face that, you have quite a service challenge there, right? You have to scale up, you have to scale down. So we need some mechanism to really firstly package everything together what we need for an application. Let it be the deep learning libraries and the CUDA libraries for GPUs, but also, of course, then on the other hand, the scale out and scale in dynamically, and of course, doing it in an automatic fashion. You don't want to have administrators then logging into each and every single node of a large cluster to install there something. And this is the automation, this kind of container automation we will talk about, which then quickly leads to something which we call orchestration. So you have a lot of containers around, almost like a big ship on the ocean, which has hell a lot of containers, and you need someone to look through all of these containers and to know what's happening there. One tool for this in the open source domain, which is quite nice, is Kubernetes. And we make the case for it, why it's good, why it's also going beyond virtualization together with containers. And we use some interesting machine learning and deep learning examples based on PyTorch, which is a tool you don't have been heard before. It's another deep learning framework, just to also shed some light on some other frameworks which are very popular and around. Then we see a little bit what AWS services. It's not surprising that, of course, Amazon, again, if you notice already in this course, has quite some service landscape also around containers, very strong in this area, and has also very nice application examples. One of it is Cookpad, what we will look at, and then really make the case why containerized applications are really then beneficial. When we look into some advanced container concepts, I could go on and go on with you. I could always go and say, well, the same what Amazon does is Google Cloud doing, and MS Azure doing, and Alibaba Cloud doing. So here, I think the idea is to look a little bit on the specific things, right, which are there. For instance, if you look on the IBM Cloud again and Alibaba with the node strategy in machine learning on the one hand, and Alibaba as a Chinese cloud provider, which is, of course, very similar in a way to Amazon. That's not completely true, but there's a point that they have also a very broad service portfolio. But thinking about then also about, again, legal constraints, right? Now you store your data not in the US, you store your data in China. Also there, EU legislation and basically EU laws and rules don't really apply. So with this, you also have to be a bit careful again. So shedding light again on this particular sensitive issue. Then essentially, as a niche market, we have seen before every now and then that actually there are some application areas which require a lot of computing. And this is usually what engineers are doing, scientists are doing. They have some computational complex problem they want to solve. And there's a Uber cloud that we already touched upon when we looked at Advania a little bit. And they're basically HPC containers. And we will look at this again in more detail because it's a quite nice example of a niche market where a company that is the Uber Cloud actually then had done some interesting footprint really in the community and is known now worldwide for this HPC containers. The example I give there is computational fluid dynamics, which is a very strong requirement in terms of computing. And I will make the application case for it in the second part when we then come to the idea of the HPC cloud simulation examples that you really can do with containers from the Uber cloud. We basically close then a little bit with further topics like singularity, which is often used in the academic fields for containers. I don't put too much emphasis on it because the idea is rather similar. And in Mesos, it's, for instance, also very particular here for MapReduce as an example, just to say that, of course, in this area, you can everything which has worker and master strategies could be nicely used with Apache Mesos. And with this, we basically have fulfilled a lot of promises we start throughout the lectures again and again from lecture 5, 9, 10, 11, essentially through all the different service levels we looked at. And we start now with the first part of it in Docker and container management. So this brings us back a little bit to the service idea. And now if you are thinking about, you are in the right hand here, and you are a cloud provider that is operating internationally with different service in each nation to be, the one that is usually used there very often. So the more the challenge is you have a lot of broad service portfolio. Your users paying, so they want to have a high level of service, and you really cannot there put administrators in each of these different countries, in each of the different computing centers, and then let them manually install everything, let's say, node by node anymore. Essentially saying that you have so many instances running, so many services that are available, that change also in versions, that change in the, let's say, demand. So sometimes the demand is, switching to complete different service. Let's remember when, for instance, Hadoop was on the market very broadly, Apache Hadoop, and suddenly Apache Spark came along. So lots of load from Apache Hadoop in a way shifted incredibly fast to Apache Spark because it was a more powerful framework if you have the memory at hand. Now, having this all manual done is, of course, quite a challenge to do. And exactly this is the area where now the container benefits start shining alongside with some others, where you think about that virtualization in a way already can give us an image with an operating system, which is quite nice. And then I can put on this operating system essentially all I need in order to basically have my libraries there that I really require. However, I always have the operating system itself. And if you think about the migration from one operating system maybe to another, then I have a problem because these libraries are often very specifically for different, basically for different operating systems maybe. So why not introduce another abstraction layer that essentially works again on other operating systems itself and would add this idea of that you have manifests that you describe what applications you need that are then dynamically pulled basically from repositories, for instance, and then installed. From this, you have essentially the containers to be a very small size on disk because the operating system is not anymore there. You essentially have that in a different layer. And also you have a very low overhead. As I said, you maybe can even pull, and say new service should be automatically pulled for Apache Spark. It's not what the administrator has to install, then that this process will be then automized. And this is, of course, something now where this lecture is heading to. There are two parts in it, two key building blocks, essentially, that you see everywhere in all clouds these days. It's the Docker, which is the open source container technology. I'm sure some of you have heard about this already. This is an interesting way, if you see on the left-hand side, when we were talking about infrastructure and a host operating system, Then we basically had the virtualization layer, and in the virtualization layer, we had another guest operating system. And in the guest operating system, then you start the applications. You see quite a huge step. But here, in contrast, what we want to achieve is maybe we can get rid about this layer of, having this guest operating system and everything. Instead, you have, let's say, a Docker layer that then describes what actually are the libraries needed for application A. You already maybe also preload data into this. And with this, you can essentially throw the Docker container, and that is really the idea. Think about a ship or a truck or something where basically what you have here, even in, some skip in Iceland, right? Or AimSkip, think about exactly this analogy. You take the container, you take it from the ship coming to Iceland, you put it to a truck. And the content doesn't really change inside the container. All what matters is inside the container, everything stays fixed. I just change everything around it. And this analogy of the container had really a big footprint in really helping administrators to have very little work compared to just, let's say, using normal virtualization. Normal virtualization is also still there. It's not that Docker will replace or is replacing everything, which we learned in virtualization. Quite the opposite. You combine them smartly. But you can see here, and that's what we already had in one of the lectures here, which was about MapReduce. They already predefined Hadoop nodes, where we said data nodes, slave, name nodes. If you remember a little bit what we had in lecture 5, really to think about that this deployment now needs to be, in a way, just using the image and specifying, on which node I want to do this. And this is all I have. So I don't really need to do the big installation myself anymore. However, now you must come to the point and see that when I have this, it's just half of the equation, so to speak. Because what happens now with my whole cluster setup, which is a little bit here illustrated on below. So how I actually specify that this fellow here is a name node, and maybe that one is a worker node, and the other one here is, etc., etc. So you come again to the problem, even if you have Docker, it's nice, you have this interesting image, you still would be manually logging into all these nodes and installing them and pulling them now in this Docker engine. No, that's also not what's happening. So here there's Kubernetes to the rescue. That really is an orchestration service for this. So here you can really have a really automated approach to install all the cloud applications in a way that is really scalable, and also manage them with versioning updates and so forth. So we start first looking on Docker, and then we'll come a bit back to Kubernetes. Here's again the analogies. Think really about the ship coming to Iceland with lots of containers inside. And the key is really having this Docker engine somewhere, which are essentially the layout of these containers. And then you will have all the required software inside that is actually validated, that's already guaranteed to run in the specific versions together. And however the environment is, you basically can pull it to Google, you can pull the same image then basically to MS Azure, it should work. And it does in many cases. Basically, it's a way of deploying applications which is extremely broadly used in all the clouds, and enables with this, as you just have heard, a very easy migration, things we don't really talk so much about in the course, right? We rather had examples in Azure or in AWS or in the Google Cloud Platform. But if you are an application developer, you maybe want to switch at some point in time. You think Amazon's maybe too expensive. As an example, I switched to Microsoft Azure for my service offerings. Things like that. Basically, the migration by having this Docker engine is not binding you anymore completely to the cloud that you're basically using. And this is a huge step towards standardization. It's not really a standard, an open standard, but it's maybe something we can say in the moment, a kind of de facto standard in the cloud to enable really portability to different clouds. Now, again, contrasting that with virtualization, I think by now everybody has seen the difference here. You have the host operating system, on top sits the Docker engine, and here you describe what binaries and are needed and libraries for the application. And then essentially you pull that on demand from repositories, or you have some things pre-installed or pre-loaded data, but it's already, the container is in itself. The hypervisor, if you remember, was the idea of having a virtualization layer, which was very powerful. So I could put Mac on it, Linux on it, Windows on it as guest operating systems, still on one host. And with this have a virtual load basically on these systems, which really helped a lot. And now the idea is, of course, with Docker to really have a lower footprint in storage. You don't carry around the burden of all these guest operating systems anymore. And this is, of course, also then enabling you more and more to go to this vendor lock-free aspect, that no matter what is below the Docker engine, you just can quickly, shift the container. All what is important is that they have a Docker engine running. And today that belongs to the service portfolio of almost every cloud, which is, basically in this kind of leak. Here's an example where we left in lecture 9, for instance, where we said we had the idea of developers using apps, if you remember, with the Cloud SDK. There we said the whole process of really building inside the cloud with different versions of the apps, if you remember, is nicely actually supported by using the so-called app engine with Cloud Build. And of course, this builds the app then into a container and deploys the container in different versions in the different Google App Engine runtimes. So a very nice example where you can imagine you want to try out this app feature, that app feature. You have Angry Birds in 100 versions, right? But all on different containers and doing different, elements. Maybe one is using the Star Wars, the other one is using a Batman idea of, using this, or have different new figures introduced in terms of games. So the point is here really that, again, containers are not only on the software as a service level to really abstract from everything. Here you can still also to use a container strategy for your building process as software engineer. And this, of course, is a very attractive approach in clouds. Of course, a side remark, think about for everything you have to pay. It goes beyond, of course, what you have in your Eclipse, but you pay the price for it. Amazon has the same idea. So, of course, Amazon has a large registry of containers that you can actually then register the containers that you need for several purposes. Then you do your versioning, your different life cycle of the software, and then run the containers. And for this, you have basically two options in Amazon. One is the Amazon Elastic Container Service, and the other one is then the Kubernetes service we look at. And the registry is essentially, as it is, just responsible for deploying then these Docker images or these container images via different AWS infrastructure elements you see here below, and we will look at a little bit. And you see also who that is used. I just put that because I guess many of you as students will know what GoPro and Ubisoft is. They are using this fantastic idea of service orchestration inside the Amazon cloud significantly here. Basically seeing that you have different services where you can execute. In the first option, you have this AWS Fargate, which basically don't require you to do any manual resource provisioning, not specify exactly which type of tier you want in the EC2 setup or something. You really abstract from that, and that is very nice. And with this container service, just an example in deep learning applications from the Cookpad here, you see they upload a specific version of an image to this registry, which is MXNet based, a deep learning framework we also don't had before, but it doesn't matter. It does the same functionality of classification of images. You see here, it should also, of course, scale. They have 12 million photos and more about food. They have 140 users, 140,000 users, and they use this concept of Amazon a lot. While the modeling is done still in the Jupyter Notebook, all the environment is prepared in this containerized setup that we just discussed, and then deployed on different operations on the AWS platform, all based on containers, really. Now, when you do this in a practical setup in a data center, we basically combine these things. You can still run, as you see here, a hypervisor, and then in the operating systems do your Docker engines, and then do different, let's say, service offerings that might be required, especially if you have a different version of the Docker engine, and still combine it then based on virtualization with a normal setup of an operating system or a normal setup of virtualization. So you have a wild mix that is going on. And exactly the reason also, if you think about the ship again, there needs to be someone who knows where is what types of containers, right? And this is something where Kubernetes comes in. So the second part now is essentially just a little bit of slides thinking about what Kubernetes is as an open source container orchestration, saying where exactly in all the clusters worldwide I deploy what software. And it really does it in an automated way. It can take basically different software lifecycle rollouts and also roll them completely back using a master and node strategy that you a little bit know from MapReduce a little bit. The same way you have here so-called kubelets, which are then essentially the communication node that interacts with the master and then will basically make all what's happening to do the Docker environment right. So essentially that you can run the Docker containers inside these different Kubernetes nodes. You can have lots of service functionality like health monitoring of all your services. You can essentially use it for deployment. And the good thing is really, once you have this as Kubernetes, you go to the next cloud provider and it's also providing the same setup. So again, it helps significantly the migration and a very easy and fast way of really changing maybe also new releases and perform updating. Here's another example now. When we think about how you can use Kubernetes, then in basically with another service here, this is in Amazon. You said, or basically you learned before, we have this Elastic Container Registry where we upload all the images that matter for us. Now, instead of using it with the Amazon Elastic Container Service, we can also use then the open source based Kubernetes one, which gives you much more portability, right? Though that's why we have learned Kubernetes is quite important. Now this enables that you use it on Amazon, but you may later use it also somewhere else where Kubernetes is actually installed. And this is, of course, very powerful and enables you different options of really scale and also migrate to different platforms. Here's an example from Pinterest that uses actually the torch serve model. The details really don't matter for you. I just put this in for you to understand that deep learning has, of course, different model versions for inference in a production. While that you still train, you basically have lots of different trained models around, and you have to navigate and manage this also. Either if you use PyTorch for deep learning or TensorFlow, it's the same thing. It's just for PyTorch here, one example. And what you have on Amazon with the basically with this server, which is a torch serve, you can put this as a Kubernetes worker strategy and then essentially have inside this Kubernetes worker nodes this PyTorch environment and this torch serve, which is really more kind of flexible tool for serving all your different PyTorch models that are flying around. Another orchestration on another level for all your different deep learning models that you have around. Just an example, and I think everybody of you know, Pinterest has lots of things in terms of associations and billions of images to digest, essentially. And that's really, I wanted to leave here on the table for you for the first part of the lecture. I think in a way it's perhaps very simple to understand because essentially it still remains software, it still remains the packages we discussed. All what happens is now you have it really specified in the Docker environment, there are manifests. And the bigger picture is, I think, very nice in this particular video. So I don't put this here in as saying that's for MS Azure, that will be also discussed later. I think just this video captures a little bit the essence of so-called microservices we don't really touch on, also because of time, because it would need maybe another 2 lectures just to talk about microservices. But we're also leaving then with this a little bit the way of essentially cloud computing and rather move into the software engineering world where, you know, Matthias Bog and software engineering practices are taking place. But in a way, I think this video captures nicely the 3 ideas of, you know, these different levels towards going to this microservices and really have this microservices for very specific functionality. So we break here for 5 minutes and then we come back to the second part of today.